In this video, we're going to focus on thermodynamics with the ideal gas equation. So in order to solve this problem, we must first list all of the given values that we can use to work with. So it says here that we have a constant pressure of 689.5 kPa. It also says here that the volume of air changes from 0.567 cubic meter down to 0.283 cubic meter. So that gives us the values for the V1 and the V2 respectively. And lastly, the problem is asking us to solve for the change of internal energy, which we will be denoting as delta U. So the key to solving this problem is with the working equation delta U is equals to m times CV times delta T, where delta T is simply equal to T2 minus T1, and the CV will have a constant value of 0.718 kilojoule per kilogram Kelvin. Now if you noticed, we do not have a value for the T2 and the T1, which we will then have to solve for using the formula PV is equal to MRT, where rearranging for T would give us T is equals to P times V all over M times R. To solve for T1 using this formula, we just have to substitute all the values that we have corresponding to condition 1. So we have a pressure of 689.5 kPa, a volume of 0.567 cubic meter, all over M, which we do not have a value for right now, and of course R, which has a constant value of 0.287 kilojoule per kilogram Kelvin. Before we solve for the numerical value for this, we must first perform a unit analysis. So for the numerator, we have kPa multiplied to cubic meter, and for the numerator, we have mass, which we don't have a value for, so we can exclude it for now, and all we have left is kilojoule all over kilogram Kelvin. The kPa here can be rewritten as kilonewton over meter squared and kilojoule to kilonewton meter. And you'll notice here that kilonewtons will cancel each other out, as well as all the meters from the numerator and the denominator. And after all this cancellation, all we have left is 1 over kilogram Kelvin, which is simply equal to kilogram Kelvin. Now typing this all on the calculator will give us a value for T1 of 1362.18 kilogram Kelvin. And let's not forget the m that we excluded earlier on the denominator. We just repeat the same steps for T2, but we now use values corresponding to condition 2. So we still have a pressure value of 689.5, but we now have a value for V2 to be 0.283 cubic meter all over m, which is still unknown, and of course R of 0.287 kilojoule per kilogram Kelvin. Typing this in the calculator will give us a value of 679.89 kilogram Kelvin per meter. We can now return to our main working equation to solve for delta U and substitute all the values that we have. So for M, we still don't have any. For CV, we have 0.718 kilojoule per kilogram Kelvin. For delta T, we have T2 minus T1, which is 679.89 minus 1362.18, and its unit is kilogram Kelvin per meter. Now, if you notice here, the meters will cancel each other out, as well as kilogram Kelvin. And after all this cancellation, all we have left is kilojoule. And typing this all in the calculator will give us the value for delta U, which is equal to negative 489.88 kilojoule, which is of course the final answer to this problem.